All right, this is the last problem in the lab worksheet for buffers, and I've made an important change. It said that we had a 40.6 mil solution of 0.101 molar acetic acid, but we have to have, in terms of a weak acid or a weak base, we need a weak base because this right here you need to recognize is certainly a strong acid. So in this problem, you'll need to make the change. It's sodium acetate that we have reacting with HCl. Now, you know, whenever you have, in water, two reagents that can react, one being a strong acid and the other one being a weak base, you need to deal with that first. We said in the center of the video, lecture of the notes, deal with the boom. This is dangerous stuff. So I know right away that I need to consider a reaction of the strong acid with, in the case of a buffer, the weak base. Now, this is not a buffer solution. All it is some amount of sodium acetate. So I'm just going to go ahead and just put, for just brevity's sake, AC minus. I don't care about the sodium. It's just a spectator ion. The acetate would have a -1 charge because sodium is +1. And I know that dealing with this boom, we'll get to the ice table soon, I have to have this strong acid act as an acid, giving the proton to the base to make the conjugate acid. And that plus would get Cl minus. So that's going to be what we have to deal with first, and we do. Let's take and make an ice table around this reaction that happens first. So we know they give us the amount of HCl and also of the sodium acetate, the initial. We have a 0 amount of the acid, and initially a 0 amount of a conjugate base of HCl. So what again I'm going to do is going to take and determine how much HCl I have in terms of moles, and then determine how much of this I have in moles and consider that reaction as part of the change. So 20 mils is 0.02 liters, moving the decimal point. 20 mils is 0.02 liters times the 0.01 molarity, because liters times molarity is equal to moles. So I have 0.0002 moles of HCl. But I also have, and again we made that change from acetic acid, now we know it's sodium acetate. So I have 0.406 liters, and I'm going to times that by the 0.101, and that'll give me the amount I have initially of my acetate. So we have now the amounts of both reagents. Strong acid, weak base. It sometimes helps to tag these. If you're not sure, you can look it up, but just maybe tagging, if you have a buffer, what is the weak acid, what is the weak base, kind of helps you know what to pull in to your ice table. Because again, with buffers, you'll make a decision which one reacts with the boom. In this case, it's an acid. We needed the weak base, and that's all we had. Of course, the change, all of this goes away. Minus 0.00 is 2, so it's 1 to 1. One of these reacts with one of these. Sometimes you had a diprotic acid. It took 2 of these to react with H2SO4. But it's 1 to 1 here. So we can say minus 0.002, and then, of course, plus 0.002. And I don't really care about the chloride, because when it comes to finding the acidity from Ka, we don't need to worry about the chloride. So at equilibrium, of course, this will be 0. This will be, let me just go ahead and do that, minus the 0.0002. For this one, we get 0.0039006. And of course, we have for over here, we have the amount then of weak base left and the amount of weak acid made. And because they give us Ka, now I'm going to go ahead and use the Henderson-Hasselbalch equation, because I realize that we can maybe use that more quickly if we do that, so it's A minus over, sorry, plus, okay, plus log of A minus over HA. That Henderson-Hasselbalch equation we're using here instead of going through a longhand version of this calculation. I'll make sure I have that right. All right, so we can take and determine pH more directly. So let's go ahead and set that up. We know A minus, that's going to be right here. This is our weak base. It has the negative charge. We have our HA, that's right here. So we can plug this in. Using the Henderson-Hasselbalch equation, we can find the pH. So pH is going to be equal to the negative log of our Ka, which is 1.8 times 10 to the minus fifth, plus the log of A minus, which in this case is our 0.0039006 over concentration of HA, and we'll be able to find our pH. So we have, I'm going to take the log of that. Get 1.2901, we'll stop there. And that's going to be, I guess, added to the negative log of 1.8 times 10 to the minus fifth. And so it's going to be a negative, make sure I got that right, just a second, 1.8 minus 5. So we're going to take the log of the negative log because it's the Ka, we take the P of it. P is negative log. Oh, okay, good. I thought it was off a little bit. So it's going to be 4.7447 because its answer of the log of this is minus 4.7747, other sig figs. But we're going to change the negative sign to a positive sign because of the negative of the negative. So we get 4.744, and we're going to add to this 1.209. Or sorry, 1.2901. So I'm going to change the sign of this. Oops. I'll just go ahead and start off with this. 4.7447. 4.7. Okay. 4.7447 plus the 1.2901 equals 6.035 is our pH. Now, just to make sure this kind of makes sense, we're adding acid to, we're taking the sodium acetate and using it to react with the HCl, and we're still going to have some of that sodium acetate still left. So we're going to have quite a bit of it. We're going to have quite a bit of that sodium acetate still left. So it's going to cause the pH to be higher because that pKa 4.74, we add 1.29, it's going to still be with a significant amount, much more than the acid. We should have a higher pH than just what would be the pKa. So this kind of is making sense. It does fit the picture where HCl has reacted with some of this, but not all. We still have quite a bit. 0.0041 minus this is still very close to 0.0041. And we have just a little bit of that acid. So we would expect the pH to go up compared to just the pKa, because Ka would be, if it was the pH equals pKa, it means these are equal to each other, but we don't have that. We have a whole lot more of the A minus than we do have the HA. We'd expect then the pH to be a little bit higher because we still have a lot of that and had that base. And that's true. So that helps to kind of make sure you're getting the right numbers. It just seems to make sense fitting the picture or the problem you have. Thanks. Bye-bye.